I will start with the actual situation. And today in this weather briefing, I will focus on I think we can still call it relatively new RGB, the Cloud Type RGB. So here you can see it, it's really an eye catcher, but not only that, it's also really a powerful RGB. But one has to admit it's also a bit complicated, or one can say tricky. And just to warm up, to start getting into this weather briefing, I would like you to take a star, take a pencil, whatever you want, because I have a question for you. It's quite an easy one, so don't be nervous. I just want you to tell me which color do you think is the most common? And I only want you to concentrate on red, green, and blue. I know there's also yellow and other things, but what do you think is the most common color, red, green, or blue? So take a pencil, take a star, and you can see on the right side of the satellite image the colors. I think I have already given you the rights to annotate. Okay, yeah, something is coming. Okay. I will give you some more seconds. Okay, thank you very much. Now, at first, let's reveal the channels behind the colors. So, wait a moment. I have to stop annotating. Okay, and so this is the recipe of the Cloud Type RGB. As you can see, it looks quite simple. No brightness temperature differences, just single channels. It can only be used during daytime due to the visible wavelength range. And yeah, most of you said that blue is the most common color. I think it's safe to say it's not green. And I think it's a tight race between red and blue. But let's take a look at what the colors mean, or what's behind each color. So let's start with the red beam, which is near infrared 1.3. And this physically relates to the cloud height. And that means that high-level clouds have a large red contribution. And that is also one main aim of the Cloud Type RGB, monitoring or detecting thin high-level clouds. On the green beam, I've already mentioned there's not so much green in this image. You have the visible 0.6, and this physically relates to cloud thickness. That means that the green channel has a big contribution for thick clouds, and also snow-covered land, like you see here in the northern parts of Norway, for example. Last but not least, we have the near-infrared 1.6 and the blue beam, and this physically relates to the cloud phase. And especially thick water clouds have a large blue contribution, and you see lots of thick water clouds at today's RGB image. So you have cloud height, cloud thickness, and cloud phase, so everything you need to know to identify the specific cloud types. But let's come back to the thin cirrus clouds, which is one main aim of the Cloud Type RGB. But as you probably know, we already have other RGBs with the purpose of highlighting thin cirrus clouds. And you can see here the dust RGB, the cloud phase RGB, and the true color RGB. And what do you think? It's another quiz. Which of these RGBs is also very good when it comes to detecting thin cirrus? You should have the annotation rights by now. You should find a star, pencil, whatever. Yes, it should be possible for you. Okay. Okay, I see some first answers appearing. So don't be misled by the name. That's my hint for this question. Don't be misled by the name. I will give you some more seconds. I think at the moment, cloud phase looks like it's okay. No, dust RGB. Okay. Just a few more seconds and that's it. So it's indeed the dust RGB. I know the name. It focuses on dust, which you can nicely see in the southeastern part of the image. There, this pinkish feature is a nice dust outbreak. But another goal of the dust RGB is to highlight thin cirrus. And you can see thin cirrus in black colors, dark red, brown reddish, and yes. But now let's compare a region with thin contrails with these three RGBs. Yeah, you can see here, this is the Iberian Peninsula, and we have here this region of contrails that can be seen really good in the dust RGB, those black streaks. You can also easily detect them in the Cloud Type RGB, but if you take a closer look, or even if you take a closer look at the true color RGB, you can only think where they are, but you have not so much details as with the dust RGB and the Cloud Type RGB. So yeah, you can see why those two are really the best tools for monitoring or detecting thin cirrus. Another benefit of the Cloud Type RGB is you can see, if you take a look at the clouds west of Mallorca, you can see those little cloud features over here. And in the true color RGB, it's only two clouds. You cannot really say, what is it? Is it water clouds? Is it ice clouds? And in the dust RGB, you can at least say, okay, the southern one is thin cirrus cloud. But when you take a look at the Cloud Type RGB, you can see it quite easily that the southern one is a thin cirrus and the northern one, the bluish one, is a water cloud, mid-level water cloud. So yeah, so the Cloud Type RGB, the name is really clear. You can easily say what cloud type it is. Okay, I have told you in the beginning that the Cloud Type RGB is a little bit tricky or complicated. And the reason for this is that the color of the feature can change depending on lower-lying clouds or lower-lying features, but also due to the moisture content of the atmosphere. And there's a really good example for this in this image. So if you take a look here to the Bretagne, to the western part of France, here you can see, I will make it a bit bigger for you. So we take a look at this feature here, and you can see it's one cloud, but it changes its color from yellow to red to yellow again. And that's due to the clouds that are above or the things that are below these cirrus clouds. So we have here water clouds below, and this cirrus structure looks yellow. Then there are nearly no clouds, then it gets red. And here we have some mixed phase clouds, and it gets, again, yellow. So that's the tricky thing. So when using this RGB, you always have to see the context. Because, for example, yellow colors can indicate many different kinds of clouds. So it can either be a mid-level thick ice cloud if a dry atmosphere is above the cloud top. If the atmosphere above the cloud top is moist, then those clouds appear greenish. You can see it, for example, over here. There are some of these greenish clouds. Yellow can also indicate thick high-level ice clouds. You can see them in the northern parts of the image, over middle France. And yellow can also be a sign for thick high-level ice clouds above lower-level clouds of snow. That's what we have seen here in the region of the Bretagne. Or yellow can also mean that it's snow on mountains, but in a dry atmosphere. Because in this image, the snow on the mountains always appears greenish because the atmosphere is moist. But if the atmosphere is dry, it can also be a sign for snow. So it's a quite powerful tool, but you have to know the context. And in the end, I just wanted to take a closer look at the dust over the Arabian Peninsula and Iran. And that's when you can see here the Arabian Peninsula, there is the Iran, and somehow I did not switch to the dust RGB, but I stayed with the Cloud Type RGB. And then I saw these interesting cloud features over here. So you see this whitish to slight pinkish cloud streaks over here. And that's now another quiz for you. Let's see that you can annotate. So what do you think? What are these, these cloud features over here? What do you think? What's this? Are those Lee waves, dips, that means dust-induced baroclinic system, or are those chemtrails? What do you think? Okay, I will give you another few seconds before we stop this quiz, because I see most of you have chosen the right answer. I mean, I was just kidding, you know, there is no such thing as chemtrails. And the correct answer is Lee waves. But how do I know that those cloud features are Lee waves? Okay, at first, I took a closer look at the timely shift of these cloud patterns, and they stay stationary. Then you have to know the topography of Iran, but in the western part of Iran, there's the so-called Zagros Mountains. And at the moment, we have a westerly flow in this region. And last but not least, the color. So this light pinkish color, this indicates thin supercooled water clouds, and most of the time, Lee waves, they are thin supercooled water clouds. So that's also a nice feature that you can detect with the help of the Cloud Type RGB. You cannot see the dust in this RGB because it's not good for monitoring surface features. But yeah, I think this is also very interesting to see. And before I come to the outlook, I will hand over the microphone to Andreas. And in the end, I will give you a short outlook on the following weather situation.
Yeah, thank you very much, Lily. In preparation of this meeting, I had a talk to Lily last week, and she mentioned that there's a drought in Central Europe. And I took this topic to see why there's this drought. And I came across the blocking high situation that we had in April for several weeks. And this will be the topic now for for the second presentation, for my presentation this afternoon. So I started with the Copernicus Climate Bulletin that is issued every month. And here it is. It first states about the average temperature, which is again too high. April was again the third warmest April since a long time. Then in blue, they mention a little bit the ice extent on the sea, which is below average as it is expected because of the climate warming. And finally, in yellow, you see they mention a persistent high pressure area over Central Europe and Western Europe. So this persistent high pressure area has an effect on clouds, has an effect on precipitation, and that's what I have, or what I want to show you from the perspective of the satellite meteorology. But there were also some areas with a little bit more precipitation, far in the east, Caucasus, and also on the western side of Spain. And well, you will see it in a few seconds. So it started end of March, early April, with this typical situation. You see here the isentrops for 500 hectopascal, and you see the high pressure area over Central Europe. And on both flanks, you have typically a low pressure, one on each side, or maybe two on each side, depending, but at least one on each side, flanking the high. So this was the beginning of the month, April. I superimposed also the jet. The jet is the factor that is responsible for the variability of the weather. So when we have a strong east-westerly component, the weather changes rapidly. But if it's a more meridional component, like here, the jet goes mainly from south to north, or from north to south here, then the weather is very stationary, doesn't change a lot, and stays the same over a longer period. So this kind of circulation is also called a low index circulation. What are the reasons now for this blocking? And there are essentially four reasons. You see here the satellite loop. This is an older loop from 2008, but it's very similar to the situation in April. In Central Europe, we have no clouds, an area that is under high pressure, and where clouds, if they entered in this area, are suppressed, are dissolved, and all the systems stay outside. You have an upper, a low pressure system over Spain, and another one here over Eastern Europe. So first thing that we see is low temperature contrast in such a situation between the polar region and the mid-latitudes. And in such a case, the jet is there, but it's not a jet that is in east-west direction. The jet is merely undulating, meandering between the southern and northern positions. That is because the temperature contrast between the polar region and the mid-latitude regions are not very high. The jet follows the Rossby waves, so we have high amplitudes of the Rossby waves, and if this is the case, then Rossby waves do not move very fast. If the Rossby wave is short, then it moves faster, but long, high amplitude waves do not move usually that fast and tend to be stationary. And the winds are mainly meridional, so from northern or southern directions. We have, and this can be seen here in the schematic on the bottom of the slide, we have these two flanking low pressure systems. It can be more than two, but these are very important because it feeds the high pressure area with energy. So they move the air to the north and bring vorticity towards the higher latitudes. And we have a thermal reinforcement. That means sinking air masses heat up the atmosphere from the bottom to the higher area. And if we have such a warm atmosphere, we have higher pressure. So it's a self-sustaining process. The warmer, the more high pressure in all levels, and we get a reinforcement of the high pressure area. So end of April, there was still this high pressure area here, as you can see here. Now it's moving, shifting a little bit to the north over the North Sea. Still, what we can see here, and sorry, I go back because I didn't mention here what we see the water vapor image, and what we can clearly see in the water vapor image is if the air is dry or not. And as you can see here, the image is a little bit darker, so we have very dry air in the center of this high pressure area. So there are no clouds, there's not much humidity, and this makes also that the sunshine is coming quite unfiltered to the ground. I took also the total column water from ECMWF for the same weather situation, and you see, of course, in the polar air here in the north and the polar air coming down here to the south, it's quite dry, but also in the center of this high pressure area, the air is quite dry. The most air is here on the western flank. It's pushed northward around the high pressure area. And on the eastern flank, we have the colder air that comes down, cold and dry air comes down to southern regions. So, and for sure, also the temperature is important. We have this typical dipole. We have cold air in the east, and we have warm air on the western part of Europe and below the high pressure area. So such an omega situation as we have it here is usually followed by a temperature contrast between an area that is quite cold in the east and quite warm in the west. And here's the temperature anomaly chart also from ECMWF, where you can clearly see the temperature anomaly, the warm air in the center of the high pressure area and on the western flank, whereas in the eastern flank, where the polar air comes down to the mid latitudes and even down to Greece and Turkey, they had a lot of snow, by the way, in that time of the year. The air is quite cold. So we have really a temperature anomaly on both sides, cold and warm. I found two stations, Kosice and Sofia in Bulgaria. Kosice is in Slovak Republic. That shows also the ensemble diagram and the temperature that shows a dip. That means a period of cold air. And that is usually expected in the beginning of May. It's called the ice saints. It's typically a cold air outbreak in this time of the year, because not always because of an omega situation, but often because of a very pronounced trough that brings colder air to the mid latitudes. So this time it was also a dip of cold air, a dip in the temperature charts, but a little bit earlier. Usually the ice saints are between the 11th and the 15th May. Here we had it a little bit earlier, early May. But the phenomenon is returning every year. There was also something that I found, the overall green droughts product for Central and Eastern Europe. And here it's mentioned on this web page that there is a longer lasting dry period, and it started already end of December with lacking precipitation over Central Europe and Eastern Europe. And the duration is now quite long, over 100 days for the 20th April. But it was ongoing then, and it's still. We had some precipitation in the last weekend, but barely enough to compensate the dry time that we had before. Finally, my last slide is from the Copernicus, also the surface analysis, total precipitation for the months of April, and you can clearly see here in the chart that the total precipitation was not enough or less than usual for most of the Central Europe, especially here in the southern part of France, Italy, but also in the eastern parts of Europe, like Romania, for example, and Poland. There was a bit more precipitation here in Spain, over Ireland, and maybe southern tip of Norway, but mostly it was too dry. Same as for the surface air relative humidity, it was too dry. The surface air temperature, and here again, you see the dipole that is produced by this omega situation. We have the warm air advection over Western Europe, and the cold air advection caused by this omega blocking over the eastern parts of Europe. And soil moisture, of course, which is really relevant for agriculture, shows a minimum over most parts of Europe. So and I have two numbers here. In Germany, there was 50% less than the usual precipitation amount, and for Austria was even hit a little bit harder. Only a third of the usual precipitation amount has fallen, and there are already some implications on future plant growth and the harvest. And by the way, there is a high risk for forest fires And we had also end of April and early May some forest fires in the southern part of Austria, and they lasted for more than 20 days. And I have read in the news that they have finally been extinguished a few days before, but this is also the consequence of this very dry weather situation caused by these blocking omega situations that last over the whole April. So, and this was my last slide. Thank you very much, and I return now to Lily.
I hope you can see my screen. So let's make the short outlook, and in this case, it's a seasonal outlook, because some of you might know that a dry spring can really increase the likelihood of a hot summer, and it looks like this will be true this year. If we take a look at the seasonal forecast charts from the ECMWF, you can see that the outlook for the summer is really hot. So wide parts of Europe have a big likelihood of a too warm and also a too dry summer. And these forecasts were initialized in the beginning of May. So we can hope these forecasts might change, but I don't think that they can change all the way. So it looks like this summer will be really hot and dry. And yeah, it's the problem with the precipitation and the moisture looks like it will increase in the coming month. And that's it from me. I can only encourage you to look further into the Cloud Type RGB. Although it is really complicated, it's really a powerful tool. And I would like to thank you for your attention with this RGB. It did not really fit into my presentation, but it beautifully highlights the power of RGBs, because you can see here the Alpine Ridge, and in orange colors you can see snow on the Alpine Ridge, and in the whitish colors in the valleys you can see the fog. And yeah, you can easily distinguish between snow and fog with this RGB, with the snow fog RGB, which you could not do with just a normal visible or infrared image. So yeah, good that we have RGBs, and that's it